Hello everybody, welcome to the second practice example where we're going to solve for a perfect Bayesian equilibrium. Now this example is going to be very similar to our first example, just that the payoffs have changed. So I'll give you just a second to go and pause the video to write this game down, and we'll move to the next slide. So as before, we're going to follow 4 steps for solving this game. We're going to write this game in an induced strategic form. We're then going to look for all possible subgame perfect Nash equilibria. We're then going to solve for the beliefs that support possible perfect Bayesian equilibria, updating those beliefs whenever possible. We're then going to define perfect Bayesian equilibrium of this game. So as before, we're going to write this game in an induced strategic form. We're then going to solve for all subgame perfect Nash equilibrium of this game. Since our game does not have any proper subgames, every Nash equilibrium that we're going to find is going to be subgame perfect. Solving this using our Tick and Bob algorithm, we find, as before, our subgame perfect Nash equilibrium is going to be where player 1 is playing left and player 2 is playing left as well, and player 1 is playing right and player 2 is playing right here. Next is that we're going to solve for the beliefs that support our perfect Bayesian equilibrium, updating them wherever possible. Now this is going to be the same comment I'm going to be making as before. What's novel when solving for a perfect Bayesian equilibrium, player 2 has a belief with regards to the actions that have been played by player 1. In this case, player 2 believes that player 1 has played L with a probability of P and M with a probability of 1 minus P. What we do with those beliefs now is that we compute the expected payoff player 2 gets from playing left and with playing right. We see in this case, however, that the expected payoff of playing L for player 2 is going to be higher only when P is greater than 1/2. Now, from player 1's perspective here, there is a little bit of uncertainty here. So what has to happen is that we need to go and think about, well, what is player 1's expected payoff from playing left and right if player 2 is acting randomly? So for player 1, his expected payoff from playing left is going to be either 4 or he's going to be getting 0 in this case, because we don't know what player 1 is going to do. Similarly, if he's going to be playing M, he is going to be getting a payoff of 3Q in this context. So let me speak that out a little bit more clearly. Player 1 is going to get a payoff of 4Q for playing F, and M, for playing M, he's getting a payoff of 3Q. We see that for player 1, playing left is going to be a higher expected payoff than playing M for any belief Q that player 1 has greater than 0. Now, because of this belief that player 1 has, right, that he will play L for any belief player 2 has, this updates player 2's beliefs to P equals 1, because if player 2 goes and knows that player 1 is going to be playing left, regardless of whatever is happening, he is going to be playing left as well. This brings us down to our perfect Bayesian equilibrium. This is going to have one more component because we have our strategy and belief that player 2 goes and has, but we're going to also have this belief that player 1 goes and has as well, which is going to be between 0 and 1. So again, a little bit of a clopin interval, right, where we're looking at any values that are just marginally greater than 0 all the way up to 1. And this refinement has dropped R and R prime as a possible equilibrium. So this is how we would define it here. So I hope this video helps. I will see you in the next one where we work through yet another example.